First off, I would like to manage expectations as far as socks. I only brought 2, and I feel that if I throw them at you, that's not actually going to encourage participation in my particular case. So, so thanks very much for having me. Thanks to you, John, to both organizing this. This is my second time at an AA camp event. It's been really nice getting to know some of you. My name is Sasha Aravkin. I'm an associate professor of applied math at the UW, and I'm director of sciences at the Institute for Health Metrics and Evaluation. And I wanted to come and tell you guys about some interesting work that we're doing. I'll try to keep it kind of as brief as possible. So the title is Discovering Outliers in Global Health Data. And the structure of the talk is as follows. First, I'll set the context a little bit, because health is a pretty relatable topic, so hopefully it'll be interesting to you kind of as a domain. Tell you what we've been doing in that area. And then the kind of the underlying question I've been working on for a few years. I started working with IHME around 2019, and this whole time I've been working with the math sciences team, lots of other people on understanding risk-outcome relationships. For example, how strong is the relationship between smoking, exposure, and risk of lung cancer, red meat, risk of heart disease, vegetables, how protective are vegetables from lung disease, and all sorts of questions like this. And I can tell a little bit about the kind of the approach that we've come up with. And then the other part of the talk is I want to talk about outliers in the data. As for the title, outliers is another thing that we've probably all seen. They bug us for different reasons. So part of the advantage of telling you more about the context here is what exactly are outliers annoying for the goal of understanding risk-outcome relationships. And I'll tell you kind of a technical piece a little bit, as much as I've allowed myself to get into that, because I love to get too deep into the technical pieces. I'll tell you about this one technical piece that generalizes easily to almost any other context. I'll try to show you that at the end of some examples, kind of showing you how that same piece applies to toy problems that you may be more familiar with just for fun. And so then if you have outliers in your data or want to talk to me about any other problems, that'll be hopefully set us up for that. So that's the plan. So to jump into this, how many people have heard of the Institute for Health Metrics and Evaluation? I'm just curious. Oh, cool. Yeah, so not too many people. How many people have seen the COVID forecast model that's been kind of on the news and so? Yeah, so the IHME recently has been famous for the COVID-19 forecast model, but before that, it was founded in 2007 with a mission to create the most complete and up-to-date roadmap to help policymakers and donors determine how best to help people live longer, healthier lives. And they produce a global burden of disease that tries to quantify the effect of basically the burden of disease, both in terms of years of life lost and years of disability across time and all locations, ages, sexes, and so forth. So it started in 2007 and now has 500 plus staff. At the end of the presentation, I have some links. IHME is hiring, particularly looking for researchers, some software developers, technical program managers. So some of you have been expressing some interest. Please check out that link at the end. So that's just a little bit about IHME. And then a little bit about the topic. You may have seen, recently we've been so focused on the pandemic, there haven't been too many high-profile news stories about whether red meat is good for you or not. But prior to that, you may have noticed that there's some flip-flopping in the media. There's a study comes out that says red meat is pretty bad. Another study comes out that says maybe red meat is not as bad for you as we thought. Similar things for eggs. Eggs are bad for you, eggs are good for you, eggs are good for you, but only if you live in China, that kind of stuff. So the state of the art in the nutrition epidemiology is that there's some gaps, and there's been criticism both from outside and inside the field. There's a quote from John Ioannidis in a Journal of the American Medical Association, one of the top journals, calling for radical reform. Some of the problems is when you're applying criteria to decide which studies to include in kind of general summary analyses, there's some clear subjective elements there. So if there's a room full of experts and they select which studies are really good and which studies are not so good, if you take a different room full of experts, they may come to a different conclusion. So it's low inter-rater reliability. And it's also difficult to compare domains. For example, if you make one decision today, should you stop eating red meat or start eating more veggies? You know, does that question even make sense? What should you do and why? This kind of thing. So this kind of all motivates a lot of the work in understanding dose-response relationships that we look at. So the questions, that we can ask is, well, how much does eating one burger a day increase the risk of heart disease on average? And maybe how protective is an extra serving of vegetables? And also, kind of how sure are we? So how varied are the results according to these different studies? And then, why, when the studies do disagree with each other, why do they disagree? And relatedly, if somebody gave you some funding to do more studies, which domain should we focus on? Should we have another study on effects of smoking on lung cancer, or should we focus on some other domain? So these are all some of the questions that we want to look at. So basically, I will describe in words kind of the approach that we've been working on for the last few years, and then switch off completely from the slides and kind of show you some results. So one of the nice things about working at IGN is there's a Viz team. So there's an interactive Viz tool that kind of lets you explore interactively all of these domains. So if you care about some particular area of health or nutrition epidemiology, you can go home and click through this, find the studies, look at the curves and so forth. So I will do that with you a little bit, but I just wanted to kind of explain the approach at a high level and then also set up the outliers part of the talk. So the first thing that we do is we gather all available study results. So maybe in some domains like smoking lung cancer, there's been 100 studies, and each study has produced several related groups of results, and we gather all that together. And then we estimate a mean risk curve of how extra smoking is associated with risk of lung cancer. And then we want to see how certain we are, and when we're looking at the certainty, the extent to which the studies agree or disagree with each other becomes quite important. And this is where we want to be extra careful about outliers. So I'll tell you about that a little bit. So in addition to getting the mean risk, we also want to understand a kind of a lower bound of the risk. So if the lower bound is pretty high, that's when we definitely want to worry about the risk. When the lower bound is not so high, maybe even crosses one for relative risk, maybe we want to worry about it less. And then we can summarize all of this into a star system. So 1-star risks are risk pairs where this lower bound may not actually increase past 1 at all. 2 stars is when it definitely increases somewhat. 3 stars is when we average over exposure. It's more than 15% greater compared to baseline. 4 stars, 50% greater, and 5 stars, 84% greater. So that's kind of the approach in a nutshell. So I wanted to show you some of the results and then kind of go through them as a fun topic, and then look at the outlier removal part. So hopefully that will be a little bit of fun. And then feel free to actually ask questions as we go through the results as well, if you are interested. Let me see. So this is the interactive tool. So this the tool contains the results for all the risk outcome pairs that we've published papers on so far. So currently there's 50 risk outcome pairs, but we'll be adding to this. So in the long run, and there's about 400 to 500 risk outcome pairs, like smoking versus lung cancer, in the global burden of disease enterprise. So you can go here and check out the one that you're interested in the most. So if we select something like smoking versus lung cancer, you can see what I mean here. So the graph is showing log relative risk. And you guys are a pretty sophisticated audience, so it can show you the log and not worry about it too much. And what you see right away is that there's a lot of between study disagreement here. So each of these points corresponds to a result from some study. And if we click on one point, then the number of points that are highlighted in dark gray show you the points from the same study that have been reported. So it's not as though we have individual points. Each point actually corresponds to some group of smokers compared to non-smokers. And so you see that overall, there's been a lot of different work in this particular area, a ton of results showing that smoking is harmful for you and causes lung cancer, but there's quite a lot of between study disagreement. So if we focus in 50 pack years, again, I don't have socks, but does anybody know what a pack year is? A pack year is the amount of cigarettes you would smoke if you smoked a pack a day for a year. So it's 50 times 365 packs of cigarettes. It's a pretty huge amount of cigarettes. So if you focus here, you can see that the mean log relative risk is 2.5. So you exponentiate that. That's how much you get to increase your chance of lung cancer compared to a non-smoker, but then it goes up as high as 4.5 exponentially. It's very high and as low as 0.7. So that's the issue. So what we do to try to make sense of this is we actually focus on this lower bound of the risk envelope. So if you look at the lower bound of the risk envelope, that's kind of, despite all the disagreements that the studies have with each other, we're certain that the risk is going to be at least as high as that. And so the score 0.73 is the lower bound averaged against the exposure that we've seen. So if you exponentiate 0.73, that's about 2. So basically, even though all of these studies disagree with each other a lot, you can be sure that this particular measure is at least twice as high compared to not smoking on average. And so it gets a 5-star rating. So that's how the rating system works. That's kind of the basic. Any questions about this one? Yes?
Do you rank anything about like the methodology determining, credibility of the studies they're using?
That's a great question. The question is, do we rank anything about the methodology? That's a great question. So part of this that's very important. When experts rank studies, they look at whether the study is kind of a quote gold standard study or not. So in some contexts, randomized case control studies are the gold standard, and cohort observational studies are a step below that. In some studies, if you do sufficient follow-up is a gold standard. If you don't do a sufficient study, it's a bit below that. So the way this methodology accounts for it is you can explain some of this between study disagreement through looking at covariates that quantify whether the studies are gold standard. So that piece of it is in this. Getting a little bit in the weeds. That's a really good question. Any other questions? Yes?
How do you deal with selection bias or publication bias, where certain studies are never published because the people who funded them don't want the results to be published?
That's also an excellent question. The question is, how do we deal with publication bias? That's a very good question. So publication bias, sometimes we can observe it. So one way to observe the publication bias is we can create a graph where we look at the effect size versus the reported sample size. And so when small studies tend to lean to one side, basically the only studies being published are the ones that are saying something sensational, that might be evidence of publication bias. But all we do in this current pipeline is we flag for that possibility. So that's a, yes.
So did you use any automated tool to extract all this information?
That's it. So the question is, do we use an automated tool to extract information? So right now, a lot of this work is happening manually. So there's data analysts who go through all the different articles. And a lot of the tasks is first searching for all the possible abstracts that may have to do with this and then windowing the abstracts down. So there's definitely targets for automating some of the systematic part of getting from the published articles to the ones that actually are included in the studies. But that automation process is not complete yet. But people are very excited about that possibility. Yes?
You're looking at attribution, basically even for the cancer, lung cancer. There could be so many other attributes. They could be drinking, their health conditions, food habits, genetics. There are so many other attributes. How do you discount them and only look at smoking?
That's a great question. The question is, how do we account for the fact there can be other explanations? So this is a meta-analysis process, so all it can do at its base is it can take results of studies. So to the extent that the studies have adjusted for anything, the meta-analysis process then summarizes those results. But we're often like fighting with one hand tied behind your back, because instead of having individual level data, so we know everybody's amount they drink, amount they smoke, what they eat, everything, we just have these, every point again is a result of a study. So in many, many contexts, we don't have, most contexts in fact, we don't have access to the detail level data. But when we do, then indeed people are very interested in, there's a field called epidemiology, so individual participant meta-analysis, when you can try to standardize how the adjustment takes place. It can decrease some of this heterogeneity and give studies more power. So all of these things are happening. So thanks. So let me pause the questions there. The questions are excellent. I think you guys are really on top of the basic piece. Let me show a little bit more that kind of sets up the outliers part. So first, red meat versus smoking is a 5-star risk. Let me show you red meat versus heart disease in the comparison, since that one is often discussed in the literature and in the news. So red meat versus stroke. Did I miss it? I think I missed it. red meat cancer, red meat. There we go, red meat versus heart disease. So here is the red meat versus heart disease result. It's quite interesting. So this gets a 2-star rating because the lower envelope, when you account for disagreement between studies, the lower envelope is sitting just around 0 in the log relative risk space, which means that if we look at it, this one we can look at linear scale, just relative risk, it would be sitting just around 1, relative risk of 1. So taking into account between study disagreement, it's plausible that you're basically at the normal. While the mean risk increases, so for example, to get to my earlier question, if you eat a burger a day, that's about 40 grams a day, you can see that there's about, on average, there's a 5% chance of relative risk of having heart disease. The variation about that is fairly high. And then if you look at the data itself, you can kind of see what's happening with the dots. There's some studies showing protective effects. Every time you have a dot that's below the line y=1, that's actually a result from a study that came back as protective, and every time you see one that's above, it came back as harmful. So this would be, you can sort of compare and contrast areas that have been studied and have pretty high results like smoking heart disease to red meat. So that's another way you can kind of use the result. Any questions on this? People tend to feel in the nutrition epidemiological community, where I'm applied mathematician, in the nutrition epidemiological community, people have really strong feelings about red meat. So I don't know if probably you guys are closer to me and not having strong feelings, but I'm always curious. You have another question?
First of all, I think this is so fantastic and so important that you're doing this. I wonder if you did the inverse of this. You take the disease and then you try to find all the characteristics that correlate most highly with the disease.
The question is, can we take the disease and find characteristics that correlate most highly? That's a super interesting question. We need a different data set for that. We need the individual line data with outcomes, so that we can do feature search. That's a great topic. It's a little bit like orthogonal, but super interesting. Yeah. Yes. Please go ahead. Yeah.
So how do we know what is the data, the amount of data that went into the analysis? Is it significant enough for the result to be interesting?
So that's a great question. So the question is the amount of data that goes in significant enough to be interesting? So for example, suppose that we have only 4 dots, but all the 4 dots agree with each other. Would we give it a high rating just because the 4 dots agree, even though maybe the 4 dots came from 2 studies, and that's the only thing that happened in the field? That's one way to interpret the question. So there's a technical detail that penalizes and gives extra uncertainty in the small study cases. So there's a problem in the field when you underestimate the effect of between study disagreement when there's too few studies, and so we take uncertainty of the estimate into account as well. But that leads down a deeper rabbit hole. But there's an element there. Thanks for the question, and then Yusha.
Okay. So how do I interpret this graph? Like, does this mean that according to the studies, red meat has like a very low correlation with heart disease, and I can continue to like eat like only steak?
So this is an excellent question. How do you actually use this? So there's several audiences for this, and one is definitely you, John. He's definitely one of the target audiences. So you can interpret this according to your risk profile. So as people will react is depending on what the risk profile is. So some people can see the same graph and react differently. So one thing you can say is, okay, I really like red meat, and if it's not huge, I'm not going to change my behavior, and that would be, you have some tolerance for risk. Somebody else can look at this and say, okay, well, it's 2-star, it's bigger than 1-star, there's definitely some effect, and because I'm risk averse, I will not continue. But the nice thing is, both of those people can actually compare this graph to say the ones for vegetables versus heart disease. So keep this in your mind's eye, and then we go back to find the vegetables versus heart disease, which hopefully low vegetables heart disease, this one. So it's also a 2-star risk, but there's a bit of a clear effect and more study data. So when you see this, Yusha, what's your gut reaction in comparison to the red meat versus heart disease example?
If if I continue to eat only steak, I should also eat a lot of vegetables.
Right, if you continue, if you continue to eat steak, so you can see there's a pretty big jump from eating no vegetables to eating 100 grams of vegetables in terms of substantially decreasing your risk by about 20%, on the average. And even though there's between study disagreement, when you take the upper envelope now, since it's protective, there's still a bigger gap there than when you saw with the red meat case. So you can start to compare them, which is pretty hard to do before. Because I don't know about you guys, but when I read a paper, like an epidemiological paper, and look through the tables, by the time I'm done looking through the tables, it's very hard to remember what it was that I was originally thinking about. Especially if you try to send this to your parents, for example, you will never get your point across. But this, you can kind of click through it, and it's really nice. Yes?
But that would still be a guess, because how those two factors interact with each other, not necessarily just adding two models together.
Are you talking about red meat versus vegetables?
Yeah, so if you add those two together in one study and you model that, you may not see that they cancel out each other.
That is absolutely true. So the comment is, if this is only focusing on one thing at a time, that's similar to your comment. If you had them all in the same data set, you might be able to know more. So there's always a fundamental limitation here. But this blew my mind when I started working in this field, is if you take something as simple as a question, how harmful is a thing at a population level? That is already a difficult question. But everybody always wants to go deeper. What happens if I eat vegetables instead? What part of the meat? Is the meat wild? Is the meat organic? Like what is, so when you start to dig down, that's what everybody wants. But even at just a core level, it's hard to answer that question, which means that we should be cautious about expecting that anytime soon, the full picture will become apparent. On the other hand, a lot of this heterogeneity could be due to different sources of meat and different quality of meat and so forth. But this is kind of summarizing what we know right now in an interactive way. Yes.
So each, like estimate for each factor, how many studies that the data come from that you are using?
So the studies can vary a lot. So sometimes there's 60 or so studies, and sometimes there's as few as 6 or 8 studies. And there's often a few points per study. Like the way these studies report their data is by comparing alternative reference groups in quintiles. So there could be 4 or 5 summary data points per study that are reported, but then the analysts scrape that then go into this to build the entire kind of curve across the domain. Yes.
So when an analyst decides to create these graphs, how do they decide on cutoffs? So for instance, like this is vegetables. What are vegetables? Or is that completely up to the analyst for determining what a vegetable is?
That is part of the study. So there's guidelines that determine which studies can be considered and which match. And then those studies describe exposure. And then there's definitely cases where different studies and fields look at exposure differently, and that must be accounted for. So there's complexities there for sure. So at this point, it's up to the people collecting the studies to say that the exposures are comparable enough or have been adjusted until we can analyze them in a single framework. That goes down a different rabbit hole. Okay, so let me pause the questions again. This is super good. Yes, I 5 more minutes. So I'm going to go, but I want to talk about outliers for just a second. So I'm going to show you one more. So I'm going to show you smoking versus aortic aneurysm and the comparison here. And then I'm going to kind of jump onto the outliers part. The outliers is going to proceed a bit fast. But this is, you guys were so engaged on the result part, I don't really mind. So the outliers on all of these are the red dots. So in every case, we automatically trim, identify, and discard a small portion of the data point. And these are labeled as red. And so in this particular graph, they're the most pleasing to the eye because you see they're farther away from the curve. So the outliers will do 2 things. First, they will move the curve up and down, which will sort of trick you. But more importantly, in this context, since we place so much stock in between study disagreement, a crappy study will inflate your sense of between study disagreement, which could doom an entire scientific area to a low star rating when most of the data is actually quite coherent. So that's why the outliers are so important. And so basically the technical piece I'm going to spend the last 2 minutes telling you about is how to automatically find and detect these outliers, and that transfers to any context, including machine learning context and so forth, if that makes sense. So it's perfect. I only have a few minutes, so even though these slides are complicated, I can pretend that the reason it's hard to understand is because I'm running out of time. Let me go to full screen. Right. So most learning problems, including large language models, deep learning, all of these things, can be cast as minimization problems. We have a sum over the data. M is the size of the training set, and theta the parameters that we're trying to learn. Okay. So, for example, it's something like a linear regression, the simplest possible thing. The two parameters are intercept and slope, and you're trying to fit a line through the data. Those are the two unknowns. In the case of deep learning, the parameters are all the unknown weights across all the layers put together. That's the data. So all of these things can be written in this form, minimize a sum of functions which relate predicted to observed data or some loss functions over the data, if that makes sense. So let's just pause there. That's just kind of how we're thinking about abstraction matters, right? So here's this biggest possible abstraction. So trimming is one of the most efficient techniques I've seen across a lot of different fields of data science and machine learning. Trimming does the following thing. It says, okay, I'm going to each data in my data set, I'm going to associate a weight between 0 and 1. And essentially, if it's found to be a 1, it means it's an inlier. If it's found to be 0, it means it's an outlier. I'm going to allow each weight to be between 0 and 1, but I'm going to force you to make sure that at least 90% of the data has to be included in your weighting scheme. So you can't set all of them to 0 and learn nothing from the data. You have to pick the 90% that you're going to set to be inliers, and then lets you ignore 10% of the data, and those 10% are the potential outliers. So it basically says, okay, instead of only looking for the parameters of the model, like slope and intercept or your neural net weights, at the same time, find me the W's for every data point that indicate is it hard to fit or easy to fit, and do those two things simultaneously. So that's the trick. So that's the approach that's used. It automatically finds the worst 10% fittable data in any corpus for any model. In the case I showed you, the model's likelihood coming from this, mixed effects model that we use for meta-analysis. In a linear regression case, it's the slope of the intercept. So here's a cool case. So you take a bunch of data, generate data from a straight line, which is a green line, and then plop a bunch of points down in the right-hand corner to be the outliers. Okay. So then if you fit these squares fit to this in the orange line, those points in the corner will crank the line down, which will give you an overestimate of the intercept, because it will go up and it will give you a negative trend, even though the overall trend of the data is a positive trend. It's a pretty extreme example. Does that make sense? You guys just like crank it down. But if you apply the trimming approach, so you allow it enough room to identify the points, then it will automatically identify these as outliers while also fitting exactly the true line for the rest of the data generating process. It's like black magic. Yes?
Why use 90%?
90% is completely out. So there's two things you can do. You either say, I'm willing to lose 10% of my data to hedge against outliers, and you have to pick the level. And that is the same approach. Or you can say, I'm going to try to figure out which of my data are inliers and outliers while I'm also doing this outlier detection. And that is possible, but you have to really trust the user to provide exactly accurate information about the data. For example, how trustworthy each data point is. And it turns out that will break in practice. Once many people start using it, somebody will provide something weird and something will go wrong. So 90% is like a default value that you can change. There's nothing special about 90%, but in practice that works really well across different domains. Yes?
I'm used to thinking about just using standard deviation.
Yes.
Standard deviation. So how is that different than?
So one thing you can do here is you can fit the orange line first, and then you can see, once you fit it, you can see which points are the furthest apart in terms of standard deviation. So then if you do that, you will tend to remove these points and also these points. And depending on how you set up the experiment, I can trick you into removing some of the good data because it's further away from the fitted line than the bad data. So that's basically the data. But what you're saying is basically the first iteration of the algorithm is exactly what you're saying, is to use the standard deviation or some other measure of how far away from the fitted line it is to then decide to neglect. Yeah. Yes?
I have a question I should have asked earlier. I'm sorry, I would like to give the questions.
Yes, okay, let me do just two more pictures and then I'm done. Okay, so it's basically this is the idea. I just wanted to show you two fun examples from toy problems. The first one, how many people have seen the eminence data set at some point in their lives, the handwritten visions? Like I'm gonna show you what the outliers look like in the eminence data set. Balance approach at risk of not being ever invited back to AI camp, because this one here clearly looks like something I've seen. So this is the worst, the hardest to identify handwritten digits from 0 to 9 in the evidence database. So that's one picture. So you can use this approach to just identify the outliers in your, machine learning training corpus. And the second figure I want to show you is the CFAR data set that has pictures of dogs and cats, for example, trying to classify dogs from cats. And I want to show you the outliers there. So this is if you have small children, this may give your small children nightmares. These are the pictures of dogs and cats that are the hardest to identify, can be considered outliers in this context. And I'm just going to end on this one. This one's my favorite. The reason it's my favorite is because it's an outlier in the following sense. It's an owl, which is a bird that definitely looks like a cat. So that's it. So so basically, as I mentioned, I actually need hiring. And then for me specifically, if you have tough problems you want to talk about or discuss, please get in touch with me. It would be really fun to talk to you. Thanks very much for your attention.
Thank you so much. Unfortunately, we are run out of time.